Hello friends, I welcome you to Learning Physics with me, and we are looking at nuclear physics, and today I want to take you to part 2 of nuclear physics, that is solve past paper questions. This is part 2 of nuclear physics. I think it should be the last, but I will give a bonus short video of, I'll call it part 3, but it will be very short, like 10 minutes. So in part 2, remember, this is part 2. Do not forget what we said we shall be discussing in this video. We said along the way in nuclear physics, we shall be discussing questions relating to mass defect, Einstein's mass energy relation, that is equals to mc squared, the binding energy, nuclear fusion and nuclear fission, and concepts of radioactivity, including decay constant and half-life. Those are some of the things we must be observing in these questions, and you must have seen such questions in part 1. So let us start part 2 very fast. We stopped, I think, on page 578 in part 1. And starting with 579, remember to have this document in hard copy so that you can always follow the videos from a hard copy document. It is better to learn that way. Okay, explain why the mass of an alpha particle is less than the total mass of two individual protons and two individual neutrons. Remember, an alpha particle is a helium nucleus. Today I will change the color of the pen. I want to use a different color. Let me use green today. Remember, the alpha particle is a helium nucleus, He42. It has two protons and two neutrons. Some energy is required to separate the two protons and the two neutrons. That is the binding energy. And experiments showed that the total mass of the nucleons is always higher than the mass of the stable nucleus. So the question is, why is it that the mass of an alpha particle, that is of the stable nucleus, is less than total mass of the individual nucleons? Of course, in separating the two protons and two neutrons, the only thing involved here is that energy is required or energy is added in separating the two protons and the two neutrons. And in bringing the two neutrons and two protons together, energy must be released. So in all cases, the mass of the alpha particle, since energy is related to mass by Einstein's equation, energy is equal to delta m c squared, energy is equivalent to mass by this expression. So if energy is given out, then the mass difference, the mass must be less. If the energy is added, then the mass must be higher. So we have two arguments. You can choose one side for the argument. You can say energy is added. Energy is added. Energy is added to separate the nucleons. Energy is added to separate the nucleons of an alpha particle. And we know that energy is equal to mc squared. We know that E is equal to mc squared. Since energy is added, so we note that the change in mass, the mass is going to be higher. So the mass is more. So the total mass of the two individual protons and neutrons, or the total mass of the nucleus, is going to be higher. We can give a reverse argument. Instead of energy being added, we know that when the nucleons are brought together, then energy must be released. So I can say alternatively, energy is released on the formation. Energy is released on the formation of the alpha energy is released on the formation of the alpha particle. And since energy is related to mass by E equals to mc squared, since energy is equal to mc squared, remember energy is released in forming the alpha particle. And since energy is equal to mc squared, if energy is released, it means the mass is also going to be less. So the mass is going to be less in this case. When energy is released, the mass is less, and that is the mass of the alpha particle formed. Then energy added to in separating the nucleons, total mass of the nucleons is going to be higher. Okay, so that is the reverse argument. An equation for a possible nuclear reaction is given: helium, nitrogen, oxygen, proton. Data for the mass of the nuclei are given in the table. Calculate the mass change in U, in unified atomic mass units, associated with this reaction. So the mass difference, delta M, is going to be the difference in the mass. For this reaction, we can check on the left. On the left, we have helium, that is 4 point, irrespective of which side is greater, you just want the difference, so I can start from any side, no problem. So on the left, we have 4.00260 plus nitrogen, that is 14.00307 minus, on the right, we have oxygen, which is 16.99913 plus a proton, which is 1.00728. That is the difference in mass. I'll just check with my calculator. Don't mind about the negative, you just want the difference in mass. So one side should be greater than the other, because if the masses are the same, then the reaction is energetically not possible. So the difference in mass is 7.4 times 10 power negative 4 in unified atomic mass units. So this is 7.4 times 10 power negative 4. Then calculate the energy in joules associated with the mass change in Roman 1. So according to Einstein's equation, energy is equivalent to mass by this expression. So we simply substitute. Difference in mass is 7.4 times 10 power negative 4 times, remember it was in U, so we change it to kilograms, 1.66 times 10 power negative 27 times the speed of light, which is 3 times 10 power 8, and this is squared. So I press my calculator. So from my calculator, I have energy as 1.1 times 10 power negative 13 joules. Suggest and explain why for this reaction to occur, the helium-4 nucleus must have a minimum speed. Suggest and explain why for this reaction to occur, the helium-4 nucleus must have a minimum speed. That is, there should be a minimum speed for the reaction to occur. Speed below that minimum implies that the reaction cannot occur. Remember that the helium nucleus is positively charged. The nitrogen nucleus is also positively charged. Therefore, if they are to freely move towards each other, it means they are going to repel each other because they are both positively charged. So that means they must have a minimum speed, which means there should be a minimum. There's a minimum kinetic energy for the reaction to occur. So you can simply say both nuclei are positively charged. Both nuclei are positively charged. Both nuclei are positively charged, so energy is required to overcome electrostatic repulsion. Because they are both positively charged, energy is required to overcome the force of repulsion between these two nuclei. Alternatively, we can look at the mass. The masses on the left was the mass of the products is actually greater than the mass of the reactants. If you look at the total, these were actually products, so the total was actually negative. I just ignored the negative. So the mass of the products is actually greater than the mass of the reactants. If you add the total mass of the products on the right-hand side, it is greater than the total mass of the reactants. So the difference is supposed to be compensated by kinetic energy of the helium. The helium should have kinetic energy to compensate for that difference so that mass energy is conserved. So alternatively, and the most appropriate, we can say that the mass of the products is greater than the mass of the reactants. So the difference is compensated by kinetic energy of the helium nucleus helium-4 nucleus so that mass energy is conserved. So remember, mass energy is one quantity. That's why I put a hyphen here. So if the mass of the products is greater than the mass of the reactants, that difference can only be compensated by one of the particles having energy, or energy being released, or energy being given to the particles. So that difference in mass is compensated by energy so that we say mass energy is conserved. Okay. Explain what is meant by binding energy of a nucleus. So we now know that binding energy is the energy required to separate the nucleons of the nucleons of a nucleus or in a nucleus to infinity. The energy required to separate the nucleons of a nucleus to infinity, in other words, separate the protons and the neutrons inside the nucleus to infinity. In other words, separate them completely that they don't experience any electrostatic force between them. Okay. Data for the masses of some particles are given in the figure. We see the proton, neutron, tritium, polonium. The energy equivalent of 1U is 930 mega electron volts. Calculate the binding energy in mega electron volts of tritium 331. So tritium 31, this one has 1 proton plus 2 neutrons. 1 proton plus 2 neutrons. So let's find the mass difference between the nucleons, the total mass of the protons and neutrons, and the mass of the stable nucleus. So the mass difference, delta M, is the total mass of the nucleons, which is 2 times, those are neutrons. Neutron number is 1.00867 plus protons, that is, it is 1 proton, so it is just 1.00728. That is the protons. So this is on the on one side. That is total number of nucleons minus the mass of this was total mass of the nucleons minus the mass of the stable nucleus, which is 3.01551. I will subtract this. So the difference here is 9.11 times 10 power negative 3 U. So since 1U is 930 mega electron volts, so I will simply say that binding energy is going to be equal to 9.11 times 10 power negative 3, then times 930. So this is giving me 8.47 mega electron volts. The total mass of the separate nucleons that make up a polonium 210 nucleus is 211.70394 U. Actually, the binding energy per nucleon of polonium. Total mass of the nucleons is this one. So we can still find the mass difference for polonium. Mass difference is going to be 211.70394 U minus the mass of a stable nucleus, which is 209.93722. Let's see the difference. So the difference is 1.76672 in unified atomic mass units. So remember, we want binding energy per nucleon. And the binding energy alone will be 1.76672 times, since 1U is 930, so this will be times 930 divided by the nucleon number, which is 210. So that is divided by 210. So 1.76672 times 930 divided by 210. So this is giving me 7.82. So that would be the binding energy per nucleon. Many times when it is per nucleon, students normally forget to divide by the nucleon number. One possible fission reaction is uranium-235 absorbs a slow-moving neutron to give us barium, krypton, and 3 neutrons. By reference to binding energy, explain without any calculation why this fission reaction is energetically possible. Why is this fusion reaction energetically possible? So this fusion reaction is energetically possible if and only if we notice that the total binding energy of the products is actually higher than the binding energy of uranium-235, or total binding energy on the left hand side. And if that is possible, then the nucleus of uranium can be able to disintegrate to emit nuclei which are more stable with a higher binding energy. So we just look at total binding energies for both krypton and barium. Total binding energy. The reaction is only possible if the total binding energy of barium and krypton is greater than binding energy of uranium. If that is not the case, then the reaction cannot really occur. I think this color is not very good. Let me check darker green. So this reaction can only occur the reaction, this is nuclear fission. Nuclear fission results into nuclei of higher binding energy. So we expect that total binding energy of barium and krypton, the word binding energy does not apply to the neutron because it's just one particle. There's nothing to separate. So total binding energy of the barium and krypton should be higher than the binding energy of uranium for this reaction to be energetically possible. Next, define half-life. Define half-life. We now know what half-life is. The time taken for the number of atoms, number of nuclei, the activity of an isotope. Which one should I use? Time taken for the number of nuclei in a given sample to be reduced to half or to one half. To one half of its initial value. To one half of its initial value or to reduce to half of the original value. That is half-life. It's actually the time taken for the activity of an isotope to reduce to half its original value. Time taken for the number of atoms in a given sample to reduce to half of their original value or to half of its original value. So that is half-life. So here you can put atoms. Here you can put activity. Depending on what you wish. All that means half-life. Time taken for the number of nuclei. Nuclei is plural, not nucleus. Number of nuclei in a given sample to reduce to half of its original value. Calculate the number of iodine 131 atoms in 1 kilogram of this water. So we know that activity is equal to lambda times n, and the activity is 400 and what was the activity? The activity is 460 becquerels. So we shall say 460 is equal to decay constant. The decay constant was, they gave us half-life as 8.1 days. Remember, we know that decay constant, lambda is ln of 2 over t1/2. So this will be ln of 2 divided by the half-life. Half-life is given as 8.1 days. So I will change it to, since we want The activity is in becquerels, so we shall change this to seconds. So this will be 8.1 times 24 hours, that is in 1 day, times 3,600, then times n. So I'm making n the subject. I'll just press my calculator. 460 times 8.1 times 24 times 3,600 divided by ln of 2. So this is giving me 4.6 times 10 power 8. An amount of 1.0 mole of water has a mass of 18 grams. Remember, 1 mole is 6.02 times 10 power 23. Molecules, atoms, nuclei, and so on and so forth. Calculate the ratio number of molecules in 1 kilogram of water over number of atoms in 1 kilogram of contaminated water. Number of atoms of iodine in 1 kilogram of contaminated water. The number of iodine atoms in 1 kilogram of this water, we have found it as 4.6 times 10 power 8. So we have our denominator there. We only need the number of molecules of water in 1.0 kilograms of water. Number of molecules in 1.0 kilograms of water. So 1 mole of water has that mass. 1 mole of water has that mass. So it means 6.02 times 10 power 23 molecules of water has 18 grams. That is the mass of that. So how many molecules are in 1 kilogram? Remember, 18 grams in kilograms, it is 18 times 10 power negative 3. So in 1 kilogram, so it means the number of molecules in 1 kilogram will therefore be equal to 6.02 times 10 power 23 divided by 18 grams, which is 18 times 10 power negative 3. To change this to kilograms. So this is the number of molecules in 1 kilogram of water. I'll just press my calculator here. So for my calculator, this is 3.3 times 10 power 25 molecules. So we now go to our ratio. The ratio is going to be 3.3 times 10 power 25 divided by 4.6 times 10 power 8. So because 4.6 times 10 power 8 was the number of atoms of iodine in 1 kilogram of contaminated water, and we have got the number of molecules in 1 kilogram. So we can just get a ratio. So my ratio is 7.2 times 10 power 16. So that is the ratio. An acceptable limit for the activity of iodine has been set to 170. So the present activity should be 170. The moment it goes to 170, beyond 170, then safety precautions should be taken. Calculate the time in days for the activity of the contaminated water to be reduced to this acceptable value. Remember, activity is going to be equal to A naught e power negative lambda times T. So we don't want to exceed 170, but the original activity is, what is the original activity? Is 4. It is 460. The original activity is 460. So this will be equal to 460 e power negative decay constant I want the answer in days, so I will leave the K constant as ln of 2 over half-life, which is 8.1 days, then times T. So I just want to find it. Remember, the K constant is ln of 2 over T a half. So I just want to find T. T will be equal to ln of 170 over 460, again divide by ln of 2 negative times 8.1. I just made T the subject. So when I press my calculator, I get this as 11.6, or approximately 12 days. Another method that we could use, another alternatively, we can find n. N is equal to T over T a half. But remember, activity, present activity is a half power n times n naught. So I'm introducing the logarithm, so it will be n ln of a half is equal to a over a naught, which is 170 over 460, and remember I have introduced ln. So n is going to be ln of that divided by ln of 2. So 170 divided by 460, I get the ln of the answer, divided by ln of 0.5. So n is, I'm finding n as 1.436, that is n. But remember, n is T over T a half, and I want T. So it means T is going to be n times T a half, n times T a half. And T a half was 8.1 days, so this will be 1.436 times 8.1. So this is times 8.1, and still it gives me T as 11.6 days. So you can check and see which method is easier for you. An isotope of an element is radioactive. Explain what is meant by radioactive decay. It is 3 marks. Radioactive, that is random and spontaneous. Normal radioactive decay results into emission of alpha, beta, and gamma radiations, and of course as the nucleus gains stability. So when someone talks about radioactive decay, this refers to the spontaneous and random. Spontaneous and random disintegration of a nucleus. This is normally accompanied by the emission of alpha particles, beta particles, and gamma radiations. So that's radioactivity. Of course, the resulting nucleus is going to have a higher binding energy per nucleon, or it will have a higher binding energy. So the spontaneous, radioactivity is spontaneous, meaning it is not affected by any external factors in the environment. We also said radioactivity is random because we cannot predict. If we have a sample of nuclei, we have nuclei in a given sample, all we are sure is that one of the nuclei is going to decay next, but we cannot single it out. So that's why we say radioactivity is random. So the spontaneous and random disintegration of a nucleus accompanied by the emission of alpha particles, beta particles, and gamma ray photons is what we call radioactivity. Remember, this results into the nucleus having a higher binding energy. Okay. At time t, a sample of radioactive isotope contains n nuclei. In a short time delta t, the number of nuclei that decay is delta n. So in a short time delta t, the number of nuclei which decay is delta n. So we can say what remains is n minus delta n. State expressions in terms of the symbols t, delta t, n, and delta n for the number of undecayed, that is what remains. Present is n. In a time delta t, what decays is delta n. So what remains is n minus delta n. So this is undecayed. Then the mean activity of the sample during the time delta t. Remember, activity is the number of nuclei decaying per unit time. The number of nuclei decaying decaying is delta n in a time delta t. So activity is going to be delta n divided by delta t. Then the probability of decay of a nucleus during the time delta t. Remember, decay constant. The probability of decay, the event is delta n. That is the nuclei which is decaying. Then sample space is actually n. So delta n over n, that is probability that a given number of nuclei is going to decay. So probability of decay is delta n divided by n. Then the decay constant. Of course, probability of decay per unit time is the decay constant. So this will be delta n over n, again divided by delta t, which gives us delta n divided by n delta t. In other words, we get probability over time. That's why we have delta n over n times delta t, probability of decay per unit time. That is decay constant. The variation with the time t of the isotope, of the activity A of a sample of radioactive isotope is shown in the figure here. So you see here it reaches first half-life, second half-life, and the third half-life is there. The radioactive isotope decays to form a stable isotope S at time t equals to 0. So the radioactive isotope is emitting S. So at t equals to 0, S is also 0. S has not been emitted. There are no nuclei of sample S of S in the sample at t equals to 0. So the graph is starting from the origin. On the axis of the figure 9.2, sketch a graph to show the variation with time t of the number n of nuclei of S in the sample. So we can draw a rough sketch here. Suppose we start with 20 isotopes, radioactive isotopes. When this reduces to 10 radioactive isotopes, it means it has emitted, the number of particles emitted must also be 10. So it means the graphs will meet at half-life. When this reduces to another half, which is 5, it means the number of particles emitted is now going to be 10 plus 5, which is now 15. That is 3/4. So on the second half-life, the other one will be actually 3/4. And 3/4 could be somewhere around here. And when this one reduces any further again, maybe to 2.5, the other one n becomes 15 plus 2.5, which is now going to be 17.5, and so on and so forth. So it means the graph is going to go like that. The graph is going to go like that. Okay, so on the axis of the figure, sketch a graph to show the variation with the time t of the number n of nuclei of S in the sample. So we have already seen how the graph would look like without wasting time. When t equals to 0, no nuclei is present. When t equals to half-life, the number of nuclei is the same as the number of the parent nucleus. And at 2 second half-life, this one reaches 3/4, N reaches 3/4. So this will be somewhere here. And the second half, the other one at third half-life. So this is going to be approximately here. So when I sketch my graph, I think 3/4, this is this. So the graph will be like that. The graph will be like that. Number of nuclei emitted goes on decreasing. As the other one, as the parent reduces by half, those which are emitted are equivalent to half. As the parent reduces to 1/4, the other one increases by 1/4. That is a half plus 1/4, and so on and so forth. So the curve would look like that. The power for a space probe is to be supplied by the energy released when plutonium-236 decays by the emission of alpha particles. The alpha particles, each of energy 5.75 mega electron volts, are captured, and their energy is converted into electrical energy with efficiency of 24%. Calculate the energy in joules equal to 5.75. I think that is easy. Energy is 5.75 times, we remove mega electron volts is 1.6 times 10 power negative 13. So I press my calculator, and this gives me 9.2 times 10 power negative 13 in joules. The number of alpha particles, calculate the number of alpha particles per second required to generate 1.9 kilowatts of electrical power. Calculate the number of alpha particles per second required to generate 1.9 kilowatts of electrical energy power. So we know that power is equal to energy over time. Energy will be equal to the number of alpha particles times the energy of each alpha particle, then divide by T. So we want the number of electrons per unit time. But remember, the energy is converted into electrical energy with an efficiency of 24%. In other words, only 24% of the energy of the electron is useful. The efficiency is 24%. So the useful energy will be 24% of this, the one which is obtained there. So the number of electrons, number of alpha particles per unit time, I'll use capital N this time. But no, I don't want to use capital N for alpha particles. So the number of alpha particles per unit time is going to be equal to the power divided by energy. The power is 1900 divided by the energy. The energy which is converted into electrical energy is 0.4%. That is the efficiency. So this will be 9.2 times 10 power negative 13 times 0.24. That is 24% of this energy is what is converted into electrical energy. So I'll press my calculator. So from my calculator, I'm getting 8.6 times 10 power 15. Number per second is 8.6 times 10 power 15. I'll check again. 900, 0.24 times 9.2 exponent negative 13. So 8.6 times 10 power 15. per second. Each plutonium-236 nucleus on disintegration produces one alpha particle. In other words, the number of plutonium disintegrating must be equal to the number of alpha particles emitted. Plutonium has half-life of 2.8 years. Calculate the decay constant in per second of plutonium-236. So we know that decay constant is ln of 2 over T1/2 or over half-life. So this is going to be ln of 2 divided by 2.8, that is in years. We want the answer per second. We can assume 1 year is 365 days. That is 24 hours. That is 3,600. So we just press our calculator. So this is going to give us 7.85 times 10 power negative 9. 7.85 times 10 power negative 9 as the decay constant. Use your answer in A Roman 2 and B Roman 1 to determine the mass of plutonium required. Use your answer in A Roman 2. In Roman 2 we have a number of alpha particles emitted. In B Roman 1 we have a decay constant. So we know that activity is equal to lambda times n. Activity is lambda times n. So n was the number of alpha particles. We saw the number of alpha particles emitted or required to generate that power per second. So n is equal to decay constant, which is activity, which was 8.6 times 10 power 15. That was the activity. The number of alpha particles required to generate that electrical power per second, that was activity. Then divide by the decay constant, we have got it from B, which is 7.85 times 10 power negative 9. This is going to be the number of nuclei, or the number of alpha particles required, or the number of disintegrations required. So this is 8.6 divided by 7.85. So this is 1.09 times 10 power 24. That is number of nuclei of plutonium, which is equal to the number of nuclei of alpha particles needed. Then we want the mass. Remember, mass divided by the molar mass is equal to the number of nuclei over Avogadro's number, which implies that the mass we are looking for is going to be number of nuclei, which is 1.09 times 10 power 24 divided by Avogadro's number, which is 6.02 times 10 power 23 times the molar mass. And the molar mass of plutonium is 236. So that is 236. I've just pressed my calculator. So from my calculator to two significant figures, this is giving me 430 grams. Remember, I didn't change this. I can check this again. 1.09 exponent 24 divided by 6.02 exponent 23 times 236 grams. So I got an original value of 427.3 grams. and I decided to write it to two significant figures. Remember, don't write answers to less than two significant figures unless they are exact or unless required. The minimum electrical power required for a space probe is 0.84 kilowatts. Calculate the time in years for which the sample of plutonium in B will provide sufficient power. The minimum power required is this. When it goes beyond this, there will be no power. I mean, the space probe will not be actually in function, or it will not be having sufficient power. But remember, the original power is 1.9. So remember, activity is equal to A naught, or x is equals to x naught, e power negative lambda t. So since it is power, we'll say power present at that time is equal to the original power, e power negative lambda times t. So the power should not go beyond 0.84 kilowatts. But the initial power is 1.9 kilowatts. Kilo is cancelling, so that's why I'm not including it. E power negative, the decay constant is 7.85 times 10 power negative 9, and then the time is t, and we want t. So I'll just press my calculator. 0.8 divided by 1.9 ln, then divide by negative 7.85 power negative 9. So I'm getting the value of t. Of course, for those who don't do mathematics, this is ln of 0.84 over 1.9 equaling to negative 7.85 times 10 power negative 9, then times t. So you divide both sides by t, and I've got 3.3. Alternatively, you can use the simple formula where you know that t, the number of half-lives is t over t a half. Number of half-lives is t over t a half. I hope we have half-life. Half-life was 2.8 years. So all we need is to find n. And remember, p will therefore be a half power n times p naught. So I'm introducing ln. N times ln of a half is equal to p, which p is 0.84 over p naught, which is 1.9, and this is under ln of that. So I'm finding n 0.84 divided by 1.9, get ln of the answer, divide by ln of 0.5. So n is 1.18. That is n, but I want t. So t is going to be n times half-life from this expression here. So t is n times half-life, which was 2.8, and this gives me 3.3 years. Okay. Radioactive decay is both spontaneous and random. State what is meant by spontaneous decay. We have said spontaneous decay, not affected by external factors. Not affected by external factors. When I talk about external factors, these include temperature, talk about pressure, talk about catalysts. So all those ones do not affect the decay. So we say decay is spontaneous. Then random means we cannot predict which nucleus in a given sample will decay next. So that is random. We can't predict. You are sure a nucleus will decay, but you can't single out which nucleus will decay next in a given sample. Okay, strontium 90 is an unstable nuclide. The activity of a sample of 1.0 kilograms of strontium 90 is 5.2 megabecquerels. Determine the decay constant lambda of strontium 90. So decay constant, of course, since we don't have half-life, we can't find decay constant from half-life. However, we know that activity is equal to lambda times n. So we can find decay constant from the activity. Let's look for the activity. The activity has been given as 5.2 megabecquerels. All that is remaining is n. Remember, we have already seen that n over Avogadro's number is equal to the mass over the molar mass. So this implies that our value for n is going to be the mass. The mass is 1.0 times 10 power negative 9 kilograms divided by the molar mass. The molar mass is 90, but it has to be changed to kilograms, so 90 times 10 power negative 3. Then cross multiply Avogadro's number, that is 6.02 times 10 power 23. So I press my calculator here to find n. 1.09 exponent negative 9 divided by 90, sorry, 1.0 so this gives me n as, my value of n is 6.69 times 10 power, this is power what? Power 15. That's times 10 power 15. So now I can find the decay constant. So the decay constant is going to be the activity divided by n. So this is going to be, activity was given as 5.2 megabecquerels. So that is 5.2 times 10 power 6 to change it to becquerels or per second, divided by 6.69 times 10 power 15. 5.2 exponent 6 divided by 6.69 exponent 15. So this is 7.77 times 10 power negative 10 per second. So I can even write this as 7.8 times 10 power negative 10 per second. The activity of the sample after time of 1.0 half-lives, after time of 1.0 half-lives is found to be greater than the expected 2.6 megabecquerels. So what is expected is 2.6, but what is observed is seen to be greater. Suggest a possible reason for this. Of course, if it is greater, then we can talk about background radiation. But most important, the daughter nucleus is unstable, is also radioactive. So the nuclei could also be also radioactive. In other words, unstable. Since they are unstable, they are most likely going to disintegrate and emit further electrons, which increases the activity. Okay, so since or there could be background radiations. You could also refer to the random nature and so on and so forth, but those are the most important ones. Explain what is meant by binding energy of a nucleus. So at this point, we know that binding energy is the energy required to separate the nucleons of a nucleus to infinity. In fact, it is the minimum energy required to separate the minimum energy required to separate the nucleons of a nucleus to infinity. That is binding energy. The following nuclear reaction takes place. We see uranium is absorbing a neutron to form CS, Rb, and Y neutrons. Determine the values of X and Y. So we just balance the equation. Balancing the proton number, on the left-hand side we have 90 plus 0 should be equal to the other side we have 55 plus X plus Y times 0. So this is 0. So it means X is going to be 90 minus 55, which is 37. Is it 37 or no? This is 90 to not 90. So it's 92 minus, let me see, 92 minus 55, I think that is 37. Then Y, we are going to conserve the nucleon number. We have finished this one, is 37. So nucleon number, we have 235 plus 1 for the neutron on the left-hand side should be equal to 144 plus, we have 90 for Rb plus Y times 1, which is Y. So we have 236 minus 140 minus 90, which gives me 2. So Y is 2. State the name of this type of nuclear reaction. It starts with uranium absorbing a neutron. So we can call it induced nuclear fission. Induced nuclear fission. Starts with uranium absorbing a neutron and it's breaking into nucleons of or nuclei of smaller nucleon number. Compare the binding energy per nucleon of uranium-235 with that of cesium. It is binding energy per nucleon. So you see that uranium-235 has a much greater nucleon number, so its binding energy per nucleon is most likely going to be smaller. So binding energy, I'll write Be for binding energy. Binding energy per nucleon is smaller for uranium than uranium 235 than for cesium 144. Since uranium has a higher nucleon number or has a bigger nucleon number. Okay, because binding energy per nucleon means dividing the binding energy by the nucleon number, a nucleus with a large nucleon number is most likely going to have a smaller binding energy per nucleon. So uranium has a smaller one. Yttrium 90 decays into zirconium 90, a stable isotope. A sample initially consists of pure yttrium 90. Calculate the time in days when the ratio of the number of yttrium nuclei to the number of zirconium nuclei would be 2.0. Okay, so yttrium decays into zirconium, a stable isotope. It means initially there was only yttrium, and then it decayed to give us zirconium. A sample initially consists of yttrium 90. Calculate time in decay in days when the ratio of the number of yttrium nuclei to the number of zirconium nuclei would be 2. In other words, we want, if we say the ratio of the number of yttrium 90 to the number of zirconium is 2. The half-life of yttrium is actually 2.7. So if currently, how should I simplify this? Okay, so when the ratio is 2, it means we are going to have 2 yttrium nuclei correspond to 1 zirconium nuclei. That is when the ratio is going to be 2. So it's in other words, it's going to be 2/1. 2 yttrium and 1 zirconium, since yttrium is on top. So the ratio, we want the ratio of number of yttrium 90 nuclei to the number of zirconium 90. We want the time when it would be 2. That is when we have 2 yttrium against 1. So the current ratio should be the current ratio should be 2 yttrium to 1 zirconium to 1 zirconium. So the total ratio is actually going to be 3. So if there are 2y and 1z, it means initially total ratio initially it was initial or total ratio is actually 3. So total ratio is actually, total would be 3 nuclei. So we shall simply use the simplest expression, x is equal to x naught e power negative lambda t. So presently we have 2 being equal to original, which is 3 e power negative lambda times t, but decay constant lambda is equal to ln of 2 divided by t a half. Ln of 2 divided by t a half, that is the decay constant. So it means we have 2/3, that is 2/3 is equal to e power negative ln of 2 over the half-life, which is 2.7, and this is times t. Introduce ln both sides, so ln of 2/3 is going to be on the right hand side, we only remain with the power, negative ln of 2 divided by 2.7 times t. So when I press, I will just divide both sides by ln of 2/2.7, and this gives me 1.6. I mean 1.6. That's 1.6. Alternatively, if the ratio is 2, that means 2 to 1. So the total is actually going to be 3. So it means original is going to be 3. That means if I know that 2 that is present is equal to a half power n times 3 that is at that time initially, then this means I can find n. N is going to be, mathematics. So this means 2 over 3 is going to be equal to a half power n. I'm just doing another alternative here. So we try to find n by introducing ln. So we say that ln of 2 over 3 times n, of course. No, ln of a half times n is equal to ln of 2 over 3. I try to find n. So I'll say ln of 2 over 3 divided by ln of 0.5. So I find the value of n as 0.585. Then I try to find t, because now t will be n times t a half. So this will be 0.585 times t a half, which is 2.7, times 2.7, which is 1.58, or approximately 1.6. Okay, so this is quite a technical question, but if the ratio after some time is 2.0, and remember it must be reducing, then it means, 2.0, that is 2 over 1, then it means initiality we can consider it to be 3, total to be 3, because it is 2 zirconium against 1 Z, so total is 3. Okay. Iodine 130 radioactive isotope with the decay constant 9.9 times 10 power negative 7. State what is meant by radioactive. Of course, something is said to be radioactive if it can disintegrate randomly and spontaneously, accompanied by emission of alpha, beta, and gamma radiations. So the ability of an unstable nucleus to emit ionizing radiations such as alpha, beta, and gamma radiations randomly and spontaneously, that is being radioactive. So ability of an unstable nucleus to emit ionizing radiations that is alpha, beta, and gamma radiations randomly and spontaneously. That's what we mean by being radioactive. The nucleus can emit alpha, beta, gamma radiations randomly and spontaneously. Then the nucleus is said to be radioactive. Then decay constant, this one is the probability of decay of a nucleus per unit time. Probability of decay of the nucleus. Probability of the decay of a nucleus per unit time, that is decay constant. Some water becomes contaminated with iodine 131. The activity of the iodine 131 in 1 kilogram of water is 560 becquerels. Determine the number of iodine nuclei in 1 kilogram of water. So we know that activity is equal to decay constant by N. So the activity is 560. Decay constant is decay. We want to find the number of decay constant. What is 9.9? Okay. So decay constant is 9.9 times 10 power negative 7, then times N. I'll just press my calculator. So for my calculator, N is 5.7 times 10 power 8. Regulations require that the activity in 1 kilogram of water is to be less than 170. You don't go beyond 170. Calculate the time in days for the activity of the contaminated water to be reduced to 170 becquerels. So we know that activity is equal to A naught e power negative lambda times T. The present activity should not go beyond 170. The incident is 560 because the activity must be reducing with the time. So this should be e power negative. Decay constant is 9.9 times 10 power negative 7, then times time t. I'm introducing ln, so I have that ln of 170 divided by 560 should be equal to, when I introduce ln on the right hand side, I only remain with the power negative 9.9 times 10 power negative 7 times t. So what is t? So t is 1.2 times 10 power 6 in seconds. We want the time in days. Remember, 1 day is 24 hours. 1 day is equal to 24 hours, which is times 3,600 seconds. So what is that time in days? So we shall divide that time by 24 times 3,600. So I have 1.2 exponent 6 divided by 24 times 3,600. So this is giving me time as 13.8888 or 89 days, which is approximately 14 days. Okay, there's always another method. So A is equal to a half power n times n naught. We find n. So n times ln of a half is going to be A, which is A is 170, n naught is 560. I'm finding ln of that. So I'm trying to find small n, that is number of half-lives. So open bracket, ln of open bracket 170 divided by 560 divided by ln of 0.5. So n is 1.72. But remember, time is n times t a half. So I will multiply n 1.72 times the half-life. What was the half-life? What was the half-life? Oh, we don't have half-life. That means I have to go back. Half-life is ln of 2 times decay constant. So I'll say times ln of 2 divided by decay constant, which is 9.9 exponent negative 7. So I get the same answer. Again, I change it to days, which gives me still 14 days. Define nuclear binding energy. So we have already seen that this is the energy required. Energy required to separate the nucleons of a nucleus to infinity. Energy required to separate the nucleons of a nucleus to infinity, that is binding energy. Explain what is meant by nuclear fission. Now we are used to this. Explain what is meant by nuclear fission reaction. So since it is 2 marks, of course, fission, that is a heavy nucleus or a large nucleus splitting into 2 lighter nuclei of approximately the same size with a higher binding energy per nucleon. It can be initiated by a neutron, or neutrons can be released in such a reaction, as we saw with uranium. So a heavy nucleus splits. Heavy nucleus splits into a lighter or 2 lighter nuclei of approximately the same mass or same size with a higher binding energy per nucleon. With a higher binding energy per nucleon. Normally it is initiated by neutron bombardment. It is initiated by neutron bombardment. And many times neutrons again are released, and neutrons are released during the reaction. So I give all these details just in case the question has 3 marks. A heavy nucleus splits into 2 lighter nuclei of approximately the same mass or equal size, but with a higher binding energy per nucleon. Normally it is initiated by absorption of a slow-moving neutron. That's why we have all along been calling it induced nuclear fission. And many times in every reaction, several neutrons are produced, which also further the reaction or proceed the reaction. That's why in class your teacher must have mentioned or have called it the unaccelerated chain reaction. A student suggests that one possible nuclear reaction is Fe absorbing a neutron to give Fe293717 Cl. The binding energy per nucleon of a nucleus varies with the nucleon number. Use this variation to explain why this reaction would not result in an overall release of energy. When you look at iron 5626, iron is almost one of the most stable nuclei. Therefore, binding energy per nucleon is almost maximum at iron, or at around 56, or nucleon number equal to 56. So the product of splitting ion nucleus must have a lower total binding energy. And if they must have a lower total binding energy, then the reaction would require a net input of energy rather than a release of energy. So binding energy um, per nucleon is maximum at around nucleon number 56. Binding energy per nucleon is maximum around when I write A, that is nucleon number, at around A equals to 56, that is nucleon number. Binding energy per nucleon, and remember iron is having nucleon number 56. The product of splitting iron must have a lower total binding energy if this reaction is to occur. And if they are to have a lower total energy, then the reaction will require a net input of energy. So products of splitting the products of splitting ion, or products of splitting Fe 5626 nucleus must have a lower total energy. Must have a lower total energy or lower total binding energy. Because it is maximum at around 56, the products are therefore having a lower total energy because it is maximum at around 56. And if they are having a lower total energy, then the reaction means there should be an input there should be an energy input rather than being released. And the reaction would require a net input of energy. So the products have a lower total energy because binding energy per nucleon is maximum at around nucleon number 56, which is for iron. So if the products have lower nucleon number than 56, then they should be having lower binding energy. And therefore, if they have lower binding energy, the reaction is not possible unless there is a net energy input in that reaction. Okay. The decay of a sample of radioactive isotope is said to be random and spontaneous. Explain what is meant by the decay being random. So we said random, we cannot predict which nucleus in a given sample will decay next. cannot predict. Which nucleus in a given sample will decay next? Then spontaneous. We said spontaneous is not affected by environmental factors. Decay of a nucleus is not affected. Is not affected by environmental factors. Is not affected by environmental factors such as temperature, pressure, etc., or chemical catalysts, and so on and so forth. So those ones do not affect the decay, so that's why we say it is spontaneous. Radioactive isotope X has half-life of 1.4 hours. Initially, a pure sample of this isotope X has an activity of 3.6 times 10 power 5 becquerels. Determine the activity of the isotope X in the sample after time of 2.0 hours. So we have that activity we know that activity is equal to A naught e power negative lambda times T. And we also know the decay constant is equal to ln of 2 divided by T half. So just now substitute, I'm just going to substitute in that expression. So activity is going to be A naught, which is 3.6 times 10 power 5 e power negative ln of 2 divided by half-life. Half-life is 1.4 hours. I will not change this. So this is 1.4. Then times T, which T is 2 hours. So time has not changed. The units have cancelled. So I press my calculator. So from my calculator, I'm getting this as 1.3 times 10 power 5. Alternatively, I would use activity is equal to A naught and a half power n, where n is the half-life. So I find n is the number of half-lives, which is T over T a half. Time is 2.0 hours, half-life is 1.4. So it means activity is going to be 3.6 times 10 power 5, then multiplied by a half power n, which n is 2.0 over 1.4. It is power n, which n is that. It is not times, it is power. So I just press my calculator. And that gives me the same answer. The variation with the time t of the actual activity A of a sample in B is shown in the figure. Okay. The initial activity of the isotope X is 3.6 times 10 power 5 becquerels. So we are starting with 3.6 times 10 power 5 becquerels. Use the information from B to sketch on the axis the variation with the time t of the activity of a pure sample of isotope X. So we have seen that at half-life, the activity is, of course, at half-life, the half-life is 1.4. Let's look for 1.4. 1, 2, 3, 4. So this is 1.4. And when it is 1.4, we have seen at half-life, the activity is going to be, of course, it reduces into 2 at half-life when it is 1.4. When it is 0, this is 3.6. After half-life 1.4, it reduces to 1.8. Then 2.0 hours, that is 2.0 hours, we have seen it is 1.3. So I'm going to just plot those 2 points. The first one is 0 and 3.6. Then 1.4, it is 1.8. 1.8, 1.8. I think 1.8 is here. 1.8 is there. Then after 2 hours, it is 1.3. After 2 hours, 1, 2, 3. I think 1.3 is there. So now just join a smooth curve through these points. These are enough for us to come up with a smooth curve. I'm trying to draw this smooth curve. You can also try to draw yours. Yeah. Although this is not very smooth, maybe I can try to make it more smooth. It is not easy on a computer. So the second graph will be like that, just below the first graph. It starts from 3.6. So we have just sketched those values for isotope X, and I think those are easy. When t is 0, the activity is that times 10 power 5. Half-life, it is 1.6 times 10 power 5. 2 hours, we have seen that the activity is 1.3 times 10 power 5. Suggest an explanation for any difference between the actual activity of the sample shown in the figure and the curve you have drawn for the activity of the isotope. So we see that the activity of the sample is actually greater than the activity of X. The actual activity is greater than the activity which has been observed. So there must be an additional source of the activity. Actually, the actual activity is greater than the expected from the graph. So what is expected is the one which is below. So something should come up with an explanation for this. So the activity of the sample is greater than the activity of X. Is greater than the activity of X. So there must be additional source of activity. So there must be an additional source of activity. And this could be the decay product of the isotope X could be radioactive, such as the decay product of isotope X So since there is a difference between the actual activity and the one we have just drawn here, the one we have drawn is what has been the one we expect, but what is actually greater. So it means there must be an additional source of activity, and such as the decay product or the daughter nuclei could actually be radioactive. Therefore, it also undergoes disintegration. Okay. State what is meant by mass defect. Mass defect. So of course, mass defect, we have been always subtracting masses on both sides of the equation. So this is the difference between the mass of the nucleus and the mass, let me say, and the total mass of the constituent nucleons, where nucleons are separated to infinity. So if the nucleons of a nucleus are separated to infinity, the difference in the mass of the stable nucleus and the total mass of the nucleons which have been separated to infinity is what we are calling the mass defect, or the mass difference, or the mass excess. Okay, so that is the mass defect. Difference in the mass between mass of a stable nucleus and total mass of the nucleons, the constituent nucleons, when the nucleons are separated to infinity, where nucleons are this is very important, where the nucleons must be at infinity from each other. Some masses are shown in the table here. Proton is given, neutron is given, helium is given. Show that energy equivalence of 1U is 934 megaelectron volts. So we know that energy is equal to mass difference times c squared. Of course, we now know that 1U is the same as 1.66 times 10 power negative 27 to change it to kilograms, times the 3 times 10 power 8, and this is squared. Because that energy is in joules, I'm going to simply divide this energy by 1.6 times 10 power negative 13 to change it to mega electron volts. So this gives me 933.7, which is approximately 934 mega electron volts. show that the binding energy per nucleon of a helium nucleus is 9.09 mega electron volts. So we need the mass defect. The mass defect is going to be the difference in the masses of the nucleons and that of the stable nucleus. So helium-4 is H42. It has 2 protons and 2 neutrons. So the mass difference is going to be 2 times the mass of a proton, which is 1.00726, plus the mass of 2 neutrons, 1.008665, minus 4.001506. So we subtract here. So this is giving me minus. So the difference in the masses is 0.03037 in unified atomic mass units. But remember in part 1, 1 U is 934 mega electron volts. So I will just multiply. But remember it is binding energy per nucleon. So binding energy per nucleon is going to be 0.030376 times 934, that is binding energy in joule in mega electron volts, divided by the nucleon number of helium, which is 4. Change it to binding energy per mega electron volts. So I'll just check the calculator here. So this gives me 7.09 mega electron volts. Okay. So remember this was helium He42. 2 protons, 2 neutrons. So we multiply to find total mass of all the protons, total mass of all the neutrons. Then we subtract the mass of the stable nucleus. Isotopes of hydrogen have binding energies per nucleon less than 3 mega electron volts. Suggest why a nucleus of helium-4 does not spontaneously break to become nuclei of hydrogen. Isotopes of hydrogen have binding energies per nucleon of less than 3 mega electron volts. Suggest why a nucleus of helium-4 does not spontaneously break down to become a nuclei of hydrogen. Of course, remember maximum binding energy per nucleon is around 56. Now, if helium-4 breaks spontaneously into hydrogen, then still it means it has actually higher binding energy per nucleon than hydrogen. You can even see from above here. The binding energy per nucleon of helium-4 is greater than that of hydrogen. A nucleus just spontaneously breaks down into nuclei which have higher binding energy in order to gain stability. So this reaction is not possible. So we can simply say binding energy per nucleon is much greater. Binding energy per nucleon is much greater. That is for helium-4. Binding energy per nucleon is much greater, so it would require a large amount of energy to separate the nucleons in helium. So it would require a large amount of energy. It would require a large amount of energy to separate the nucleons in helium. So you see, for hydrogen it is 3 mega electron volts, but to separate the nucleons in helium is around 7.09 mega electron volts, according to what we have seen. So helium-4 does not spontaneously break down into a nuclei of hydrogen. In fact, it is more stable than the nuclei of hydrogen, so it can't break into them. Alternatively, you could also say the amount of energy released in forming hydrogen isotopes is less than the energy required to break apart a helium nucleus. Amount the amount of energy released in forming hydrogen isotopes. The amount of energy released in forming hydrogen isotopes is less than the energy required to break apart a helium nucleus. So that is all we could say. Hydrogen, any nucleus which has a higher binding energy cannot easily spontaneously break down into a nuclei of lower binding energies. One possible nuclear reaction that takes place is uranium absorbs a neutron to give MOLA 2 neutrons and 7 beta particles. Data for nuclei in this reaction are given here. Show that the energy equivalent to a mass of 1.00 U is that. I think we have now showed this. Energy is equal to mc squared. 1 U is 1.66 times 10 power negative 27. Speed of light, that is 3 times 10 power 8, and this should be squared. That energy is in joules, so we divide this by 1.6 times 10 power negative 19 to change it to kilogram. I mean to mega electron volts. No, it is negative 13. Negative 13 to change it to mega electron volts. I hope I didn't change. Yeah, negative 13 to change this to mega electron volts. So I press my calculator. So from my calculator, I am getting 933.7, which is approximately 934. Uranium, use data from the figure to calculate the binding energy per nucleon of a nucleus of uranium 235. Complete the figure. So we need to find the binding energy per nucleon. Let's check the mass defect is 1.86 U. So the binding energy is going to be 1.865 times 1U is 934. So times 934. And binding energy per nucleon is now going to be 1.865 times 934 divided by nucleon number, that is 235. So I press my calculator here, 1.865 times 934, 235. So this is 7.41 mega electron volts. So that is the binding energy per nucleon of uranium-235. The nucleon number of an isotope of the element rutherfordium is 267. State whether the binding energy per nucleon of the isotope will be greater than, equal to, or less than the binding energy per nucleon of uranium-235. So you see that the nucleon number of rutherfordium is 267, and yet that of uranium is 235. So that of rutherfordium is greater than that of uranium. Since binding energy per nucleon we divide by the nucleon number, so it is going to be less. That is less than. Calculate the total energy in mega electron volts released in this reaction. So we need to find a difference in energy. We need to find a difference in energy on both sides of this equation. So we have mass defects. We can use mass defects to find the total energy. We get the difference in the masses on both sides. On the left hand side we have this one. On the right hand side we have this one. So we can get that difference. Then we multiply it by the energy equivalence. I think that is one of the easiest methods. So we can say energy released, or the difference in mass on both sides of the equation, is going to be 1.219 plus, what is that value? 1.219 plus 0.85 minus 1.865 on the other side. So on one side we have 1.219 plus 0.859 on one side, minus the other side is 1.865 for uranium. So this is the mass difference. When I multiply this mass difference by the energy equivalence, remember this is going to be in units, that is U. So that is 1.219 plus 0.859 minus 1.865. So this is 0.213 U. But remember, this is the difference in the mass on both sides of the equation above. But the energy equivalence is going to be this times the 934. 0.213 times 934. And this is giving me 198.9, approximately 199. So the energy is 199. Alternatively, you can find a difference in the energy on both sides of the equation. Let's check difference in the energy on both sides of the equation. On the left hand side, I have 236. No, I can use the energy here was 7.412. I think 7.412. 7.412 to 4 significant figures. This is the binding energy per nucleon on the left hand side. So I'll multiply this by the nucleon number to get the binding energy alone. Then I check the binding energies of these. So another alternative method for that question would be, on the left hand side we have MO, nucleon number is 95, times the binding energy per nucleon, which is 8.443, plus LA, nucleon number is 139, times the binding energy per nucleon, which is 8.189. I'm finding total binding energy on one side, minus, on the left hand side we have 7.412 times the nucleon number, which is 235. So we just subtract that. Let me check directly. 95 times 8.44 plus 139 times 8.189 minus 7.412 times 235. So the difference in energy here is the actual energy released, which is also 199. So this is method number 2. You can use the binding energies per nucleon, but you must take them back to binding energies only. Or you can use the mass differences. You get the difference in mass on both sides of the equation. And then, of course, the proton, the beta particle, the neutron, those ones are negligible. Their binding energies are negligible, so they don't matter here. So that's why I'm getting 199. You can also verify. The nuclei in 1.2 times 10 power 7 negative 7 moles of uranium all undergo this reaction in a time of 25 milliseconds. Calculate the average power released during the time of 25 milliseconds. So let's begin by finding out how many reactions occur. Remember, 1 mole of uranium has 6.02 times 10 power 23 nuclei. And remember, each nuclei is going to disintegrate. So how many reactions are those? So the number of reactions is going to be equal to 1.2 times 10 power negative 7 times the number of nuclei, which is 6.02 times 10 power 23. That is the number of reactions which are going to occur. Let's check this. So this is 7.22 times 10 power 16. Those are the reactions we expect to occur in that time. But then what is the energy released for every reaction? The energy will go to 199 mega electron volts. So energy per reaction, energy released for one reaction is going to be 199 times 1.6 times 10 power negative 13 to change it to joules. And this is giving me 3.18 times 10 power negative 11 joules. So how many reactions are those? Remember, power is energy over time. Power is energy over time. This is the energy for each reaction, and this is the number of reactions. So total energy, we multiply those two, then we divide by time to find the power. So power this is 7.22 times 10 power 16 times 3.18 times 10 power negative 11. That is the total energy divided by the time. which is 25 times 10 power negative 3. So we just press our calculator. So from my calculator, I'm finding the power as 9.2 times 10 power 7 watts. You can also verify. Radon-22 is a radioactive gas. It's a radioactive gas that decays randomly with a decay constant of 7.55 times 10 power negative 3 per hour. That's what is meant by random decay. So we now know that random decay, the decay we cannot predict which nucleus will decay next in a given sample. So random decay means cannot predict which nucleus in a sample will decay next. Then decay constant, we now know what decay constant is. That is the probability of decay of a nucleus. The nucleus per unit time. The probability of decay of a nucleus per unit time is now, that one is the decay constant lambda. The activity of radon gas in a sample of 4.8 times 10 power negative 3 meters of air taken from the building is 0.600 becquerels. There are 2.52 times 10 power 25 air molecules in a volume of 1.00 meters cubed of air. So we now know the number of air molecules in 1 meter cubed. All that we don't know is the number of radon atoms in 1 meter cubed. So we can begin by finding the number of nuclei in this volume using that activity. So we know that activity is equal to lambda times n. So the number of nuclei present in that volume is going to be 0.6 times 3,600. Okay, so people should be able to see that the decay constant, I was about to skip this step. Decay constant lambda is equal to ln of 2 divided by, which method should I use? Ln of 2 divided by T half divided by half-life. So they gave us above here, the half-life is 7.5 times 10 power negative 3 per hour. 7.55 times 10 power negative 3 per hour. So per hour, how do we change per hour into per second? Remember, per hour is like dividing by 1 hour. 7.55 times, no, this is decay constant, it's not half-life. Decay constant lambda is 7.55 times 10 power negative 3 per hour, that is over 1 hour. which is going to be 7.55 times 10 power negative 3 divided by 1 hour, which is 3,600. So it means n is going to be 0.600 divided by 7.55 times 10 power negative 3. So I just substituted for decay constant and the activities. So I made n the subject. So this is in 4.8 times 10 power negative 3 meters cubed of air. How about in 1 meter cubed? Because this activity was for that volume. So for 1 meter cubed, of air, then n is going to be, I'm going to divide this by the total volume to get for 1 meter cubed. So this will be 0.6 times 3,600 divided by 7.55 times 10 power negative 3 times, I'm dividing by 4.80 times 10 power negative 3. So that is n. Now I go to the ratio. I will not press the calculator here. I will press it just once. So let's find the ratio. The ratio is going to be number of air molecules. Remember, in 1 meter cubed, the number of air molecules was this. So we shall simply say 2.52 times 10 power 24 divided by number of radon atoms, which is this one. So I will get the reciprocal. So this will be over 0.6 times 3,600. The denominator goes up, so that will be 7.55 times 10 power negative 3 times 4.8 times 10 power negative 3. So I will press my calculator. So this is 4.2 times 10 power 17. 4.2 times 10 power 17. So that is the answer. This question had 5 marks. It involved a lot of principles. Just using the first equation, A is equal to lambda naught. Find n, those are almost 2 marks. Then being able to convert the decay constant, that is another mark. Substituting into the ratio, then finding the final answer, those are 5 marks. The incomplete nuclear equation for one possible reaction that takes place in the core of the nuclear reactor is given here. State the name given to the type of nuclear reaction. You see it starts with absorption of a neutron. So this is an induced nuclear fission. That is induced nuclear fission. Complete the nuclear equation. So we just need to balance. I'll first put there an X. We have on the left hand side, we have 92 nucleons. On the left hand side, we have 57 plus 42 plus 0, then plus X. So the nucleon number is so X is equal to 92, 57, 92 minus 57. Actually, it is 92 minus 99, which is negative 7. So this means that this is going to be E7, 0, negative 1, because the other side is it is 92 minus 97, which is negative 7. So this becomes negative 1, or it can be beta 0, -1, and a 7 in front. The nuclear number was already balanced. The mass defect for the reaction is 0.223 U. Capture the energy in joules equivalent to 0.22 U, 223 U. So we know that energy is equal to the mass difference times C squared. We convert this to kilograms, so this is 0.223 times 1.66 times 10 power negative 27, then times 3 times 10 power 8, and that is squared. So we now press our calculator. So from my calculator, squared, so this is 3.33 times 10 power negative 11. Okay, so the answer here is 3.33 times 10 power negative 11 joules. Suggest two forms of energy released in this reaction. Of course, normally energy is going to be released in form of kinetic energy of the products. Energy is also given out in form of gamma ray photons. Or it can also be given off in form of neutrinos. A neutrino may accompany the emission of the beta particles, so in form of neutrinos. Energy can be given off in form of kinetic energy of the products, gamma ray photons, in form of neutrinos. So energy can take any of these three forms. State what is meant by binding energy of a nucleus. So we now know that this is the energy required to separate. Energy required to separate the nucleons in a nucleus to infinity. It is actually the energy required, the energy released when nucleons come together from infinity to form a nucleus, or the energy released when nucleons come together from infinity to form a nucleus. So that is a binding energy. Okay. Some masses are shown in the figure. Calculate the binding energy of a nucleus of lanthanum 141. So we look for the mass difference. Delta M is equal to the difference in the masses. We know that the mass of the total nucleons is going to be greater than the mass of the nucleons, of the nucleus. So we shall lanthanum has 57 protons plus this is 84 neutrons. 141 minus 57, that is 84 neutrons. So this is going to be 84 times 1.009 plus 57 times 1.007, that is total mass of the nucleons, minus 140.911. Press my calculator. So from my calculator, I have 1.244 U. But that's not the binding energy. We want it in joules. The energy equivalence, according to Einstein's equation, is delta M times C squared. So I substitute. This will be 1.244. I change it to kilograms. So times 1.66 times 10 power negative 27 times that is the mass in kilograms times the speed of light, which is 3 times 10 power 8, and this is squared. Check my calculator. So this is giving me 1.9 times 10 power negative 10 joules. The nuclide lanthanum has a half-life of 3.9 hours. Initially, a radioactive source emits only lanthanum. The initial activity of the source is A0. Calculate the time for the activity of lanthanum to be reduced to 0.40 A0. So we know that activity is equal to A0 e power negative lambda times T. So after some time, the activity is going to be 0.40 A0. So this will be equal to A0 e power negative decay constant. They gave us the half-life, and decay constant is ln of 2 over half-life. So this will be ln of 2 over half-life, which is 3.9 times the time in hours. So I just press my calculator to find T. A0 has cancelled out. So T is going to be ln of 0.4 divided by negative ln of 2 over 3.9. So I'm finding T as 5.2 hours. Alternatively, the simplest method could be A equals to A0 into a half power N. And you can find N, all we need is to find N. So N times ln over half is equal to A0. A is 0.4 and A0 is A0. So this is 0.40 A0 over A0. So we find N. N is going to be 0.4 divided by ln of 0.5. I'm finding ln both sides, so this is also ln. So n is going to be ln of 0.4 divided by ln of 0.5. And it means I'm getting n as 1.32. Remember, n is equal to t over t a half. So it means t is going to be 1.32 times half-life, 1.32 times the half-life, which is 3.9. So times 3.9. So that gives us 5.2. So the time is 5.2 hours. Suggest why the total activity of the radioactive source measured at the time calculated in A may be greater than this. Why the total activity may be greater? These are many reasons. You can talk about background radiation, daughter product may be radioactive, the random nature of decay. So daughter Daughter product may be radioactive. Daughter product may be radioactive. You can talk about the random nature. Radioactivity is random. That is, we cannot predict which nucleus in a given sample will decay next. You can also talk about the background radiation. This may increase the activity. Background radiation. Okay, next, and I think it's the last question for this video. A sample of radioactive isotope contains any nuclei of isotope T. At time t plus delta t, the sample contains n minus delta n nuclei of the isotope. The time interval delta t is short. Use the symbols n, delta n, t, delta t to give expressions for the average activity. Remember, activity is the number of nuclei decaying per unit time. So after a time, the number of nuclei decaying is given as delta n, because if the original sample is n, and after delta n, what remains is n minus delta n, it means what has decayed is delta n. So the number of nuclei decaying, that is delta n, over the time, that is delta t, that is the activity. Number of nuclei decaying per unit time. Then probability of decay in that time delta t. Probability of decay is the event, which is delta n is decaying, sample space is n. So probability of decay is the number of nuclei decaying over the original number of nuclei. Then decay constant, that is probability of decay per unit time. So we divide delta n over n by t, and it becomes delta n divided by n times delta t. Or you can write it like this, delta n over n times delta t. So the isotope polonium is radioactive and decays to form lead. The nuclear equation for this decay is that data for nuclear masses are given in the figure as shown here. Determine for the decay of one nucleus of polonium-208 the change in U of the mass. So you can find the change in U. Polonium has a proton number 82. No, we don't need the proton number because we just have one equation. So we shall find the difference in mass on both sides of the equation. So mass difference is going to be on the right hand side we have 203.973043 plus 4.002603. That's on the right hand side, minus on the left we have 207.981245. So find the difference using my calculator. So from my calculator, I'm getting 5.60 times 10 power negative 3 in unified atomic mass units. So this is 5.60 times 10 power negative 3. So that is the mass change. And then the total energy in picojoules released. The energy equivalence to that mass defect is given by Einstein's equation delta m times c squared. And this is going to be equal to, the mass difference is 5.60 times 10 power negative 3, that is in U. We change it to kilograms times 1.66 times 10 power negative 27 in kilograms. Then times the speed of light, which is 3 times 10 power 8. That is squared. So when I press my calculator, so from my calculator, we have 8.36 times power. So this is times 10 power negative 13 in joules. We want the answer in picojoules. So pico, to bring a prefix, you divide by its value. So this will be 8.36 times 10 power negative 13 divided by the prefix is pico, that is 10 power negative 12. So our final answer is going to be 0.84, 0.836 picojoules, that is 0.84. The polonium-208 nucleus is initially stationary. The initial kinetic energy of the helium nucleus is found to be less than the energy calculated in part 2. State two possible reasons for this difference. Why is there a difference in kinetic energy? Of course, some energy is emitted in form of gamma ray photons. Some energy is given out as kinetic energy of the recoil of the lead nucleus, because the lead is going to, although polonium is initially stationary, when it emits lead, the lead may recoil or move away. So some energy is used, is kinetic energy of recoil. Some energy is kinetic energy of recoil. Kinetic energy of recoil of the lead nucleus. Of the lead nucleus. So some energy is given off as gamma ray photon. Some energy is given off as the gamma ray photon. I want to write gamma in full. Okay, so I think that is almost the end of nuclear physics. Just will be one short video of 10 minutes. Give you bonus questions from one of the tests I gave to my students. Okay, so I hope you have enjoyed this video, and do not forget to subscribe. After nuclear physics, the last topic in A level will be oscillations and simple harmonic motion. So thank you for watching this.